if I am given more than just the actual integrand, if I'm given actual values, I can figure out what these plus c's are. So the question here is to find f of x. And so we have the second derivative, general, right, with a variable still in there. And then we have specific values. We have two specific values, right? Notice it's really important that the first one is of x, the other ones are of points. And so if I take the antiderivative of the second derivative, right? If I take the antiderivative of the second derivative, I'm at the first derivative plus c, right? This is just a general statement. That is always true. You're going up a level. And so let's take the antiderivative of 2, because that's what f prime of x is, dx. Well, that's going to be 2x plus c. And so f prime of x, we know, is 2x plus c. But I also know, right, I also know that f prime of 2 is 5. So f prime of 2 is 2 times 2 plus c, which is equal to 5. Well, so 4 plus c is equal to 5. C is equal to 1. So I now know, right? I now know that f prime of x is 2x instead of plus c plus 1. And so now I can say, if I take the antiderivative of f prime of x, well, the antiderivative of the derivative would give me the original function, again, with the plus c. And so if we take the antiderivative of 2x plus 1, that's going to, you can put a parenthesis around there if it helps you kind of visualize this. Well, that's going to be 2x becomes just x squared plus x plus c. But I know, once again, if I know that f of x is x squared plus x plus c, but I also know that f of 2, which is, again, now we plug in the 2 squared plus 2 plus c, I know that that's equal to 10. I can figure this out. So this is 4 plus 2. This is 6 plus c equals 10. So c equals 4. And finally, f of x is equal to x squared plus x. I figured out the c. It's plus 4. So to recap, right, if you are given specific values of what the answers to these integral problems will be, you can go back and plug them in and figure out what that plus c is. Last one here, let's just see one example of doing this with a velocity problem. So this is something that comes up in the Delta Math and on your weekly summative. A particle moves along the x-axis with a velocity. Okay, so we are given the velocity of negative 2t minus 5 for t is greater than 0. If I'm given the velocity, and I am given the velocity function, and I am given a specific position, I can figure out where that particle moved to, right? And here's why. If I take the integral of the velocity function with respect to time, that tells me the position function plus c. Because the integral of the velocity function is going to tell us how far we moved, right? And so if I take the antiderivative of negative 2t minus 5 with respect to t, well, that's going to be t squared. It's going to be negative t squared, right, to make that negative 2 happen, minus 5t plus c. And that's going to be equal to the position function. So the position function is negative t squared minus 5t plus c. But I also know the position when t equals 0 is negative 9. That's a little confusing because they use the x there because it's back and forth along the x-axis. I know that p of 0 equals negative 9, and that's equal to c. Okay, well, hold on. Let me just make sure we see why that's happening. Negative 0 squared minus 5 times 0 plus c. c is equal to -9. And so I can take, right, p of t, I now know, is negative t squared minus 5t minus 9. And so I can plug in what is the position at time t equals 2. The position at time 2 equals negative 2 squared minus 5 times 2 minus 9. And you'd work this out. What would this be? Negative 4 minus 10 minus 9. This would be negative 23. So same idea there. Just the whole point of today is undoing power rule derivatives. And if you are given specific values of the levels moving upwards, you can figure out that c. Otherwise, it's called an indefinite integral for a reason, because we do not have a definite c value, right? It is the general form without a c value, but if you're given specific values, you can figure it out.